We've been looking at L'Hopital's rule to help us with limits in indeterminate form. So far, all we've looked at for limits in indeterminate form and using L'Hopital's rule was indeterminate form that was in the form of 0 over 0 or infinity over infinity. So recall that let f of x and g of x be differentiable on some interval I containing a, and that g prime of a doesn't equal 0 on I. For x not equal to a, then suppose that if we look at the limit as x approaches a of f of x over g of x, we get the indeterminate form 0 over 0. Or if we look at the limit as x approaches a of f of x over g of x, we get that indeterminate form of infinity over infinity. If that's the case, then we can use L'Hopital's rule that says this is the same thing as looking at the limit as x approaches a of the derivative of the numerator divided by the derivative of the denominator. And so we were using this rule to help us find limits that gave us that indeterminate form. The thing is that not all the indeterminate forms are in that form of 0 over 0 or infinity over infinity. So we may have some indeterminate forms that look like the following. These are all indeterminate forms. Negative infinity over infinity would be an indeterminate form. We just saw 0 over 0 and infinity over infinity plus or minus. If we had something like 0 times infinity, that's an indeterminate form, or 0 raised to the 0 power is another indeterminate form. Infinity raised to the 0 power and 1 raised to infinity. So if we get something that's in this form, we may or may not be able to manipulate it so that we could get the indeterminate form to look like the 0 over 0 or infinity over infinity. And if we can, then we can use L'Hopital's rule, hopefully, to help us find that limit. So let me pull up an example. Actually, I think I know one in my head. So let's look at the following. I don't see it in here. Here, let me pull it up. We're looking at the example where we're looking at the limit as x is approaching 0 from the right-hand side of x times the natural log of x. If we go in here, we do that direct substitution. Well, as x is approaching 0, that piece goes to 0. And then if you're looking at the natural log of x, and as x is approaching 0, recall that that was a asymptote there. A vertical asymptote at x equals 0. And so our function is going down to negative infinity. So we have this indeterminate form, but it's not an indeterminate form that can use L'Hopital's. So we want to manipulate this so that we can use L'Hopital's rule if possible. And so one way to do that is to rewrite this as a division problem that is equivalent. So let's look at the limit as x is approaching 0 of the natural log of x. And we can write this as all over 1 over x, right? Natural log of x divided by 1 over x is the same thing as the natural log of x times x. And so now when we go do the direct substitution, natural log as x is approaching 0, recall that was negative infinity, all over as we have 1 and over x going to 0. So we have 1 over a very, very small number that's positive, and that's going to be going to infinity. So we now have this infinity over infinity. And so we can now use L'Hopital's rule. And so we want to take the derivative of our numerator. So the derivative of the natural log of x, that is 1 over x, divided by the derivative of 1 over x. Well, recall 1 over x, that's the same thing as x to the negative 1 power. So let's take the derivative, writing it as x to the negative 1 power. So taking the derivative of x to the negative 1 power, that's negative x subtracting 1 from our exponent. to the negative 2 power. So I could rewrite this a little bit. So x is going to 0, 1 over x divided by negative 1 over x squared. Let's multiply by the denominator. So we have the limit as x is approaching 0 on the right, and 1 over x times negative, and flipping it, so we have x squared right over 1. And so we can simplify this. So we have negative x squared divided by x. That's going to just leave us with negative x. And so now looking at this, as x is approaching 0, that's going to be going to 0. Okay, so here's a case where L'Hopital's rule didn't work at first, but we were able to manipulate it a little bit so that we could use L'Hopital's rule. Okay, so looking at another example, we have the limit as x is approaching 1 on the right-hand side of x, and x is raised to the 1 divided by x minus 1 power. If we go in here, and again, we do direct substitution, we'll notice that we get that indeterminate form. This indeterminate form, well, x is going to 1 on the right-hand side, that base is going to 1. And then our exponent, that's 1 over 1 coming in on the right-hand side, that denominator is going to 0. So 1 over something going to 0 goes to infinity. So we have that indeterminate form of 1 all over infinity. Okay, so this is where we're going to want to use natural logs to help us. And so maybe we can let, I don't know, how about, I don't know, let's just say y equals x raised to the 1 over x minus 1 power. And if we took the natural log of both sides, we can bring our exponent down. And so we have the natural log of y equals 1 over x minus 1 times the natural log of x. Okay, so let's look at the limit of this right-hand side. So let's look at the limit as x is approaching 1 of this, and then another way I can write this is the natural log of x, right? All over x minus 1. And so now when I look at this and I plug in x approaching 1 for my limit, well, as I'm getting closer and closer to 1, the natural log getting closer and closer to 1 goes to 0. And 1 minus 1 in my denominator also goes to 0. So we've just manipulated this to be in the form that we can use L'Hopital's rule. And so let's go forward and use L'Hopital's rule on this. And so we have the limit as x is approaching 1 on the right, taking the derivative of natural log of x, that's 1 over x, divided by the derivative of our denominator, x minus 1, that's just 1. So technically, right, I'm just looking at the limit as x approaches 1 on the right of 1 over x. Nice. Rewriting it. And so as we do direct substitution, we see that this is 1. The thing is that this is not what we started out with. And so in order to rewrite this, we can take e, raise both sides. Basically, this is the same thing, right? We can get back what we had by looking at e to the y, or e to the natural log of y is equal to e to the natural log, just rules of exponent, or rules of logs, natural log of x raised to, actually, no, that was, yeah, to the 1 all over x minus 1 power. So when we looked at the limit of our function, x all over 1, or raised to the 1 over x minus 1 power, this is the same thing as that limit as x approaches 1 of this e to the natural log of x raised to this 1 minus x power, 1 divided by x minus 1 power. Remember, we could just take we can look at the limit of the exponent. We just found that that limit of the exponent was 1. And so this is going to just give us e raised to the first power, or just e. Okay, so the next example says limit as x is approaching 0 on the right of the quantity 1 over sine x minus 1 over x. If we look at this and we do direct substitution and think about this, remember as x is going to 0, sine of 0 is going to 0. And so if we have 1 over something getting really small going to 0, that piece is going to infinity. And so this is going to equal infinity minus, well, 1 over, again, something going to 0, that's going to blow up and go to infinity. So we get that infinity minus infinity, which is an indeterminate form. And so we want to see if we can manipulate this. Okay, so let's rewrite this. How about let's rewrite this as a single fraction? And so if we write this as a single fraction, we need a common denominator. And our least common denominator is x times sine x, right? So I need to multiply this first fraction by x over x to get the common denominator. And I need to multiply this second fraction by sine x over sine x. So looking at the limit as x is approaching 0 on the right, rewriting this as a single fraction, we have x minus sine x in our numerator, all divided by x times sine x. And so now when we do direct substitution and we plug in 0 wherever we see an x, we get 0 minus sine of 0. Sine of 0 is 0. So that's 0 all over 0 times sine of 0, which is 0. So now we have that indeterminate form. And so we're going to look at this and we're going to use L'Hopital's rule. So the limit as x is approaching 0 on the right. Now let's take the derivative of our numerator. So derivative of x is 1 minus derivative of sine x is cosine x. All over, okay, we need to use the product rule in this denominator. So product rule, so derivative of the first, derivative of x is 1 times the second sine x, plus the first x times the derivative of sine of x, which is cosine of x. So again, let's go in and do our direct substitution and see if we get something back. Well, if we plug in 0 and for x, we get 1 minus cosine of 0. Well, cosine of 0 is 1, so 1 minus 1. All over sine of 0, which is 0, plus 0 times cosine of 0, which is 1. So we're getting an indeterminate form of 0 over 0 again. we saw at the end of last class period that we might have to apply L'Hopital's rule more than once for it to come out. So let's apply this again. So we're looking at the limit as x is approaching 0 on the right. And now taking the derivative of our numerator, derivative of 1 is 0. And the derivative of negative cosine of x, that is going to be negative of negative sine x, so positive sine x. All over, so derivative of sine x, that's cosine x, plus, I'm going to need to use the product rule here on x times cosine of x. So derivative of the first, x is 1 times cosine of x, plus x times the derivative of cosine of x, which is negative sine x. So limit as x is approaching 0 on the right of sine x all over. Well, cosine x plus cosine x, that gives me 2 cosine x plus x. Actually, let's just bring the negative out. So minus x sine of x. So let's go in and plug in 0 wherever we see an x. So we get sine of 0 in the numerator, which is 0, all over 2 cosine of 0, which is 2, minus 0 times sine of 0, which is 0. Okay, this is 0 over 2, which is not an indeterminate form, and that one's okay, that one's 0. So this is telling me that the limit as x is approaching 0 to the right of our original function 1 over sine x times, or minus 1 over x is equal to 0. So our next example, we have a limit as x approaches infinity of the square root of 9x plus 1, and that's all over the square root of x plus 1. I notice if we go in and do our direct substitution right away, we have 9 times infinity plus 1, the square root of that, that's going to infinity. Same thing with the denominator at the square root of infinity plus 1, so that's going to be going to infinity. And so we have this L'Hopital's, or it's in an indeterminate form, which says I can use L'Hopital's rule if I wanted. Let's rewrite this a little bit before I do that, just to make taking the derivative a little bit easier. So we're going to look at the limit as x goes to infinity. Instead of writing it as the square root, I'm going to rewrite this as 9x plus 1 raised to the 1/2 power all over x plus 1, and that's raised to the 1/2 power. So now let's apply L'Hopital's rule. So limit as x is going to infinity. So derivative of the numerator, I have 1/2 of the inside, 9x plus 1, subtract 1 from my exponent, so that's going to be negative 1/2, times the derivative of the inside, so times 9, all over. So the derivative of the denominator, bringing our power down front, we have 1/2 of the inside, x plus 1, subtract 1 from our exponent, we get negative 1/2, times the derivative of the inside, which is 1. Okay, so notice things simplify a little bit. That 1/2 and that 1/2 cancel, right? I could rewrite this so that my exponents are positive. So if I do that, I have the limit as x is going to infinity of 9. I'm going to bring up this x plus 1 and make the exponent positive of 1/2, all over, bringing down that 9x plus 1 to make that exponent positive. So 9x plus 1 raised to the 1/2 power. So notice again, If we go in and we do direct substitution, plugging in infinity, wherever we see an x, we're getting that indeterminate form again of infinity over infinity. So we could apply L'Hopital's rule again. Okay, so taking the derivative of our numerator, bringing my power down front, I have 9 times 1/2 or 9/2 of the inside, x plus 1, subtract 1 from my exponent, negative 1/2, all over the denominator, the derivative of the denominator. So bringing my power down, I have 1/2 of the inside, 9x plus 1, subtract 1 from our exponent is negative 1/2, times the derivative of the inside, which is 9. So that 9 times that 1/2, that front is 9/2. So I notice that 9/2 will cancel with what I have in the numerator of 9/2. So again, I could rewrite this, making my exponents positive. And so, or now I have 9x plus 1 to the positive 1/2 power, all over x plus 1 to the 1/2 power. Uh-oh, if you don't see it, notice that this is what we originally started with. So notice that using this L'Hopital's rule, we're going to continue to go on this cycle, and we're always going to get this infinity over infinity. So this is a case where L'Hopital's rule does not work, and we need to figure out how to do this some other way. So recall when we got infinity over infinity before, we divided by the variable raised to the highest power in the denominator. And so we can think of this as, let's multiply by a fancy one, and that fancy one is 1 over that variable raised to the highest power that's in the denominator. So we can look at this as a limit. It's x is going to infinity. If you want to keep it as square root, you can. Square root of 9x plus 1. We're going to divide this by square root of x, all over the square root of x plus 1, all divided by the square root of x. So I'm going to use rules of radicals. If I have a square root divided by a square root, I can rewrite that as a single square root. So this is the limit as x is going to infinity of the square root of 9x plus 1 all over x divided by the square root of x plus 1 all divided by x. So let's break that down as 2 separate fractions. So if I do that, that gives me the square root of 9x over x, which is just 9, plus 1 over x divided by the square root, x divided by x is 1, plus 1 over x. And so now as x is going to infinity, and remember 1 over infinity, that value goes to 0. So we're left here with the square root of 9 over the square root of 1, which is equal to 3. So there's a case again that the indeterminate form, we had it, but L'Hopital's rule didn't work, and we had to go back and use something that we've done in the past to help us solve it.